Thank you for watching our video. I'm Naoki from Nagoya University, Japan. In this video, I will talk about LiDAR-based ego-vehicle localization applications with the persistent homology. The persistent homology is a technique used in the topology. As far as we know, this is the first study to apply the persistent homology to the localization problems. First, I'd like to share with you what does this work do. We apply the persistent homology to LiDAR-based localization applications that might utilize advantages of the persistent homology. In this work, we investigate how the persistent homology works in place recognition and categorization and global end-to-end localization problems. Unfortunately, we could not have better results. However, we believe presenting the first applications with the persistent homology could be the contribution. In addition, we discussed how we can utilize the persistent homology in localization. To share the outline of the persistent homology, first, I'd like to explain the topological data analysis. TDA is a data analysis method based on the topology. In TDA, dataset is regarded as a point cloud, and its geometry is analyzed with techniques used in the topology. The persistent homology has a major role in TDA and has been applied to many scientific applications recently. For example, this figure shows the molecular distribution of the decade and the growth. This seems to be randomly distributed. However, the persistent homology can extract specific patterns from the distributions and enables to distinguish them. To know the persistent homology, we have to know about the homology. Informally, the homology is numbers of holes in the d-dimensional space. Intuitively, the zeroth, first, and second homology groups are numbers of connected components, holes, and voids. In the topology, there is a very famous example. A donut and mag are the same. This means the homology groups are the same in both geometry. A mag is composed of one connected component and one hole. A donut is also composed of one connected component and one hole. That's why these geometries are the same in terms of the topology. In the topology, we do not focus on exact shapes of geometry. However, we have a problem. How we can compute the homology in point clouds? Because point clouds does not have boundaries, hence it is difficult to define exact shape. In the right-hand figure, there might be one connected component and four holes. However, we do not have any evidence to determine the numbers. If we can know the boundaries, we can know the connectivity of the points and can define the homology. We need a method to compute the homology while considering the unknown connectivity of the points. The persistent homology can solve the problem. Let me explain intuitive outline of the persistent homology. First, we have a point cloud as shown in the left figure. In this case, we have two-dimensional point cloud. Circles are set to the points and its radius will be increasing. In the middle left figure, the circles are connected and we can see a hole. We say this time as the hole is burst. Furthermore, the radius will be increasing and the hole is disappeared in the middle right figure. We say this time as the hole is died. Finally, we can have pairs of birth and death times. These pairs can be plotted on a two-dimensional surface as shown in the right figure. This plot is called the persistence diagram. The persistence diagram is topological features extracted by the persistent homology. The persistence diagram cannot maintain local shape information of the point cloud. However, it can abstract global structure of the point clouds. There are many types of feature extraction methods from point clouds. However, as far as we know, there are no similar methods to the persistent homology. Hence, we are motivated to use it for localization. Additionally, the persistence diagram can be vectorized. For example, the persistence diagram can be converted to an image, and this image is called the persistence image. The persistent image is kind of sum of weighted functions centering at the birth-death pairs. By vectorizing the persistence diagram, we can have several advantages. For example, we can get the same size vectors from different size point clouds. Hence, we can easily apply machine learning algorithms to the point clouds. Additionally, the persistent image is translation and rotation invariant against the original point cloud. Hence, we can easily compare point clouds via the persistence images. Furthermore, size of the persistence image is small, even though original point cloud is extremely huge. Based on these advantages, we consider the persistent homology could be utilized for the price categorization and recognition and global end-to-end localization problems. In below, I will explain how we apply the persistent homology to the applications. In the price recognition, we need to recognize the places where a vehicle already passed through. To recognize the places, the sensor measurements are compared. However, we need to consider translational and rotational changes of the sensor measurement as shown in the figure. If we use the persistence image, we can create fixed size vectors from different size point cloud, and it is translational and rotational invariant. Hence, we can easily compare the sensor measurements via the persistence image. In the price recognition method with the persistence image, the persistence diagrams are generated from their point cloud. Then, the persistence images are generated. Finally, the Euclidean distance between the persistence image is computed, and its similarity is calculated. And this similarity is used to recognize the places. This slide shows the better result of the price recognition. The colors of the trajectory represent the similarity that is calculated based on the Euclidean distance between the persistence images. In these results, the largest intersections can be exactly recognized by the persistence image-based method. The green circles represent the source poles, and the red point means high similarity poles. Such a characteristic place can be recognized using the persistent homology. However, this slide shows the bad results. Many similar places were recognized. The persistent image-based method cannot distinguish similar places. Actually, we could not have better results in other cases as well. We also apply the persistent image to place categorization. In the place categorization, we perform the Euclidean distance-based k-means clustering. In this case, the numbers of the clusters were set to 4. In this environment, we can see 3 cross intersections, and in the top left area, we can see a T intersection. The persistence image-based clustering can distinguish the different types of intersections. We also apply the very simple scan feature-based method to the place categorization. In this method, simple scan features such as lines and circles are detected, and these numbers are compared. The k-means clustering with the same cluster size was also applied. The persistence image-based clustering can distinguish the intersections. However, the simple scan feature-based clustering cannot distinguish the intersections. These results suggested that the persistent homology can be used to roughly classify the place categories. However, it is difficult to improve the accuracy of localization. We also conducted the global end-to-end localization using a convolutional neural network. In the end-to-end global localization, we try to estimate a bigger pulse from sensor measurements without any prior. CNN runs the duration of the sensor measurement and pulse. Since localization is basically performed using a map, the map should be fed to CNN. However, it is difficult to feed the map since its size is quite large. The map size easily exceeds the gigabyte size. In this investigation, we generated a persistent image from the map and feed it to CNN. Since size of the persistent image is small, even though the original point cloud is huge. We compared 2 networks. The first network, default to ARPANET, receives the sensor measurement only and estimates the bigger pulse. The second network, default to LPINet, receives the sensor measurement and the persistent images generated from the sensor measurement and map. Both the networks learn duration of the input and pulses. This table shows the test results of the both networks. LPINet slightly outperforms the ARPANET. However, drastic performance improvement cannot be confirmed. The investigation with the end-to-end localization also shows that it is difficult to improve the localization accuracy by the persistent homology. Let me summarize the experimental results. In the price recognition and categorization experiments, the persistence image-based method enables to distinguish a characteristic price and give different categories to prices with different shapes. In the global end-to-end localization, the persistence image contributes to slightly improve the localization accuracy. However, it was shown that improving the localization accuracy by the persistent homology is not easy. Basically, exact shape information is important to improve the localization accuracy, since we need to correctly match point clouds. However, the basic concept of the topology does not focus on the exact shape. The persistent homology also does not maintain exact shape of source point clouds. Hence, we consider it is difficult to improve the localization accuracy by the persistent homology. However, we believe the persistent homology could improve localization performance since there are other important metrics to evaluate localization. For example, guaranteeing stability is quite important. We believe the persistent homology could contribute to realize the performance guarantee since it enables us to abstract global structure or point clouds. To utilize the persistent homology in localization, we need to find appropriate supplemental problems. In the future, we would like to find such a problem and would like to solve it with the persistent homology. Let me conclude this work. We applied the persistent homology to the LiDAR-based vehicle localization problems and found that it is difficult to improve the localization accuracy by the persistent homology, since it cannot maintain exact shape information of source point clouds. In order to utilize the persistent homology in localization, we need to find appropriate supplemental problems. We believe the persistent homology could be utilized to improve the localization performance except for the accuracy metric. Thank you for watching our presentation video. If you have any questions, please feel free to contact me.